basically given any knowledge rules for either autonomous driving or flight or in any scenarios, such that we can leverage the knowledge, translate it to the structured and like say first order or higher order knowledge, such that we can give that to like multimodal models, either LLMs or VLMs, to leverage the reasoning capabilities of foundation models, and in the meantime, make it be able to very structured and targeted to leverage particular safety knowledge and make sure that it never violates knowledge, because otherwise we know all the data-driven models, including all the foundation models, only fit the probability distribution rather than align or complying with certain particular knowledge rules, right? So here we want to leverage or ensure both happen so that we can both leverage the good capability of probability inference plus the knowledge enabled safe inference. So here the structure on the high level, as we can see, is that, say, given multimodal input, like a video plus some text in terms of, like, say, the reason we have text here is I want to enable different tasks, which we can discuss later. Not only control task, but also reasoning, QA, these types of tasks to ensure that we can like validate the safety of the driving and like air or different control in different control environment.
But better to focus more on the demos. What will be demoed in May? And what is the demo going to show in terms of learning algorithm, in terms of verification? No need to describe now any algorithm. Just say, this is what we'll demonstrate, this is what we'll verify, and this is what's the integration between you and Louis, because we have two objectives: to show integration between the team members and also what being demonstrated through the experiment that you will show.
Okay, yeah, sure. That sounds good. That's what we discussed with Louis' team. I think Ayushi is here who will present. So basically, the plan for the demo is that we will integrate this pipeline, the knowledge-enabled foundation model safe driving, which is certified in terms of the control signal prediction, with the landing scenario and the simulator that Ayush generated, such that we give the safety knowledge rule for the landing scenario, and then we can show that the landing control signals always follow or never violate the safety rules with certified safe and robustness guarantees. That'll be the plan. Or Ayush, if you have other things to add, please let us know.
So from our end, we are primarily going to work with your group to set up the safe lander, which is the safe autos air taxi version, into the simulator, and also integrate it into our overall system. So I'll talk about it a little bit during our presentation, but the scenarios and all will be dependent on your work.
Mm-hmm. Yeah. So maybe I can quickly mention how this on the high level works, and then Ayushi, you can mention the simulation so that the landing scenario, so that we can discuss the integration. So basically, on the very high level, here the idea is that we can map certain safety rules into different structured knowledge rules. For example, if we say, okay, if we see, say, a stop sign, it should stop, or if we see a red light, or if we know, like, say, based on the distance to the front vehicles or to the land, then it should have speed smaller than certain things. So basically, all these safety rules, we translate them to different predicates, and these predicates will be translated to formula like first order or higher order logics. Like say, if you see light, you should not accelerate, you should not have left pass, and you should not like your etc. And then with all these different rules, and we will map them to the like the probabilistic graphical models, so that this graphical model will not only like ensure the rule to not be violated for the probabilistic graphical models, but also continuously will leverage the historical driving experience using like control rack based systems, so that we can leverage the driving experience and say related like driving signal from videos, etc., to extract related driving experience. And with all these components, three components together, will be enable like a high level action query. Like you can ask why the agent do such query, do such action, so that you can validate and understand the reasoning of the agent, which is pretty important for debugging purposes, for example. And then you can also have high-level justification query and the low-level in terms of the action, and the low-level justification query in terms of control signal. And in the meantime, with the control signal, of course, you can do the control of the vehicle or the agent itself. So with that, let me quickly show. Here are some examples with like different scenarios with video and text input, and then you can basically leverage, given the safety knowledge, and ensure the both high level and the low level actions, and then like make it enabled to be deployed in real world. Let me quickly show an example of the failure cases, and then maybe we can move on. So the failure case is that here, for example, if there's a driving scenario, and say if there's a control signal, like a query in terms of what's the action of the ego car, and then if the model answers it should go forward at the beginning, as we can see, then it will directly go to the post-safety validation to see which is post with knowledge-enabled probabilistic graphical models, and then you will see, because that the previous action is see the red light, see stop, and keep, so that this moving forward should be rejected. Therefore, it move back to the action planning itself, and then correct the action planning from move forward to stop, and then continuously based on this correct reasoning enabled and the rule following action, it will continue to design the following actions and the corresponding control signals. So this is a simple example of how the model could make mistakes for the prediction potentially, and then the knowledge rule will help correct it and ensure the safety security. With all this, it is possible to enable the certification because based on the probability propagated over the model will provide the lower bound of the risk guarantees. This is one important component as an example. And the second important component as an example is that how we leverage the contrast learning in terms of the driving history and like input control and query signals, such that we can extract related experience from the embedding space, and then leverage those related experience to potentially improve and like use as a context, for example, as in context learning in the multimodal prediction process, such that it can give related experience and improve the safety of the driving performance. So finally, let me show some quick examples. So basically, this is like the real world, say Berkeley BDDX dataset, and if we compare with all the existing state-of-art foundation model-based driving algorithms, like say Drive GPT, RAG Drive, etc., and from different metrics, like what we can see here is that, say, this is mean square error of the like a control signal itself, and we can see it have quite significant improvement compared with the best state-of-art models, so that this will give leverage the capability of foundation models and give a significant improvement of the driving action and signal prediction, and with the certification through the knowledge violation probability. And this framework itself is general, so that for the demo, the plan for the demo is that during any scenario, for example, the lander scenario, we will be given the safety knowledge as input, and then this framework itself will be able to build the knowledge probabilistic graph, and then provide actions which will be feedback as the action signal to the simulator again to ensure the safe lander and other safe driving scenarios. Yeah. With that, is there any questions? If not, we'll move to the next presentation.
Maybe I will add a few words about integration. The AI basically gives the rules a qualitative advisory. But to quantitatively execute, for example, like a flight, what is the wind gusts like? What direction is the wind? How to react to it? What is their weight shift? Like the certain carrying things, you have one cable, maybe loosen, so the weight, center of gravity will move. Those things, actually AI are known not to be very effective for two reasons. One reason is the loop, the AI loop is too slow for reacting for fast changes in flight. It might work in car, but certainly in fast flight, it has a lot of problems. Basically, you don't have fast enough. And then it does not have the detailed state information. For example, that we have 6 dimensions, right, for free body in the air. So how can we make sure the goal, let's say decelerate or avoid an object? You have to go through a verifiable control algorithm. So that actually is a gap we can work successfully over. So on I work with Bo and work with Naira, especially with Naira for a very long time, and work in the flight. So the best way is using the AI advisory as a control goal. So essentially, if you think about it, is if you want to guarantee anything which has been validated and certified, is through the opponent function. Unless somebody able to set, we don't need the opponent function for system stability anymore. Otherwise, for flight vehicle, the certification will run into a stonewall, because you have to build a fast dynamic. And that is not the strength of AI. The AI actually are extremely much better to discover what you need to do. But essentially, it's a detailed control goal for a particular scenario. So if the way we move forward is take the AI advisory as a optimization objective, and then all the boundaries is essentially it's a linear matrix inequalities polygon. And then we can use L1 adaptive control to enforce the goal. So basically, we treat AI is a super pilot. He or she knows what should be the right reaction. Actually, that is the AI strength. And in fact, in terms about the frequency loop, it is approximately right. In fact, it can be faster than the pilot something, but it cannot go as fast as control the engine. So if AI, just think about it, is a super pilot, and then you go through the integration between pilot and control. So the whole thing actually can be very successful. That's the way, at a very high level. Think about AI is trying to replace the pilot. And their pilot also does not directly control those low-level issues. And in fact, it cannot in a train situation. So I think it's through LMI, it provides formal mechanism to fulfill the integration. So I leave it like that. So I say it looks good. AI does the super pilot, and L1 simplex take care about the rest, including partial software fail and mechanical fail.
Okay, Louis, let's now let Ayush present, because we have also Evangelos in line and we also want to present. We basically want to share what's coming in May for demos. Ayush, are you ready to?
Yes, Mikhail from our side is going to start the presentation.
Okay, can you share now?
Yep. Just 1 second.
Bo, can you maybe stop sharing so Ayush get no
I'm
delay?
not sharing. Okay. I think I'm not sharing, right?
All right, can you see my screen?
Yes.
Yeah, Professor Louis Shao will start, give a short speech, and then we'll take over.
Okay. So the first thing is we talk about the advancement in the simulation infrastructure. And then we talk about certain at the hardware level, to make sure how can we step by step from a ground vehicle to a Quanza pilot, and eventually go to the mini home, sort of a hardware, sort of what we need to have the hardware support to make it happen. And then we will talk about how can we assure safety in a certifiable way. And we talk about how both group and my group collaboration in this big picture about the entire ULI. So, Mikhail, this is yours.
Yep. Can everyone hear me? Okay.
Yeah.
So I will start off with presenting the simulator effort. So for the May demo, we have 4 main objectives associated with the simulator. First of all, we want to achieve a basic a basic setup for the simulator, where we can have a high fidelity simulation of various vehicles with their physics simulation incorporated as part of the higher level simulation. And we also have to we also want to have some basic path planning integrated into the ego vehicle. And then the second objective, which is one step ahead of objective 1, is having a fully autonomous vehicle with the perception, planning, and control integrated into the simulator. And what I mean by this is we want to have the infrastructure ready to support any perception algorithm, any planning algorithm, and any control algorithm integrated into the simulator. Objective 3 for us for the May demo is going to be supporting multiple autonomous aerial vehicles in our highly realistic simulator. And we also want to enable tools to collect some important metrics associated with the simulator. For example, if somebody wants to run a bunch of different scenarios, they will be able to collect some key metrics associated with that. And Objective 4 is just a little bit away from Objective 3, and it is about having an interactive setup where our guests at the May demo will be able to seamlessly interact with the simulator, make their own scenarios, and see the effects immediately. So I'll just very quickly go over how the simulator works. So we have a highly realistic environment based on Carla, from which the sensors are reading off the data. Then after some pre-processing, they pass it to the planning module, which then generates the trajectory and any control that is needed by the vehicle and passes it to the vehicle module, which contains the control as well as the vehicle physics simulation, which then simulates the vehicle pose and passes this back into the Carla module to update the position of the vehicle. And we have some basic module to oversee the entire simulator. So in summer 2024, this was the state of the simulator, and currently we are almost done with it, but there is still quite a lot of work that needs to be done to be fully prepared for the May demo. And I will very quickly introduce some basic features that we currently support and which are mostly related to Objective 1 that I mentioned earlier, which is having a vehicle flying in a realistic environment. Then we also support configuration file-based editing, where by simply editing some values in the config file, you can, for example, change the starting position of the vehicle in the simulator. We also support adding obstacles to the simulator, both static and dynamic. However, I want to point out that these obstacles do not have any autonomy associated with them. We also support different vehicles in our simulator. For example, as you saw in the previous slides, we can fly the generic urban air mobility vehicle developed by NASA. And in this slide, you can see that, here you can also see that we can support the Minihawk simulation in our in the higher level in our simulator. So here's a quick overview of the features that we currently support, and as I have already mentioned, they're mostly related to Objective 1. We also have some infrastructure to support basic autonomy. As you can see on the slide, currently our simulator allows to combine perception and some very basic path planning to locate a landing pad and navigate towards it. And this was primarily implemented with the help of Professor Hyunjin's team, who provided their perception module as well as some as the path planning module. We also aim, as already mentioned, to have a multi-agent support for the May demo, where we'll have multiple autonomous agents navigating in a cluttered urban environment. And regarding the video that you now see, I want to point out that this is for illustration purposes only, and some of the autonomy components that are required to support this behavior are work in progress. And also the scenario that you just saw is clearly not really possible, neither in a simulation nor in real life. But again, this is for illustration purposes only. And we hope we will achieve fully autonomous multi-agent supporting infrastructure by May. And Objective 4, as I already mentioned, we hope to make it interactive so that the users can come up to the booth and make some basic edits in the config files that we'll set up for them so that they can interact with the simulator, see how they could use it for their own research projects. Yeah, sorry. So just to summarize the contributions of our simulator of this direction of effort. First of all, we our main contribution is that we provide a realistic simulator that supports the infrastructure that has the infrastructure to support any autonomy component, be either perception, planning, or control, which can easily be used for research in aerial vehicles, in urban environments. We also support cross-group research that has already utilized the simulator to produce several papers. We have collaborated with different groups. We have supported their research. And if you think that this simulator could help in your research, feel free to reach out. We're open to any requests to make the simulator more flexible. And now Simon will take over from here.
Thanks, Mikhail. So our demo plan for the robust and interpretable perception pipeline is laid out as 4 milestones, as shown here. The first milestone, which we plan to complete by this May, involves the design and integration of various hardware components. Specifically, we will first design, fabricate, and test the second generation biped motherboard hardware, which is updated to be capable of controlling the helicopter VTOL chassis, as shown here to the right. The next milestone, which we also plan to complete by this May, involves the planning, sensing, and control of the completed and integrated hardware. Specifically, we'll develop firmware for the completed hardware to enable some basic flying capabilities. And then we'll set up required sensors, such as image and IR sensors, together with the visualization and communication of such sensor data with our biped ground station software. During the May demo, we aim to demonstrate the complete hardware with flying and landing capabilities, as well as the functional sensors. So yeah, the next slide. So moving on to the next 2 milestones, which we plan to complete by the end of this summer, around September. The third milestone here involves the integration of safety layer software, which provides us with safe obstacle detection using IR camera by segmenting and projecting the depth data, as well as creating collision avoidance zones. In addition, we will perform fault injection experiments for the redundant hardware array setup we will have for the safety layer software. The last milestone involves the integration of mission layer software, which provides us with robust and interpretable obstacle recognition using the image camera. And our latest submission, the neuroprobabilistic circuit pipeline. Excuse me. Additionally, we'll conduct experiments evaluating the distribution-shape robustness as well as the interpretability of the NPC pipeline with various physical scenario setups, as roughly illustrated on the right, using the helicopter hardware. In the end, our end-to-end hardware software platform will enable safe, robust, and interpretable obstacle detection and recognition during vertical takeoffs and landings. Thanks. I'll hand it over to Ayush.
Thank you, Simon. So our last planned demo has to do with our work on perception simplex. The key research goal of this work is to showcase verifiable collision avoidance, even when there are obstacle detection faults in the MLA perception. The verifiable part of that is in the papers, but we'll showcase the collision avoidance. So the overall setup we will use for this is we'll use the simulator setup that Mikhail described earlier, and we'll use fault injection to emulate MLA perception faults. In this simulator, we'll set up scenarios where obstacles are within the landing path, close to the landing path, and far away. And the first goal of the demo would be to show collision outcomes when the safety layer is present versus when it is not. Note that there can be collisions even when the safety layer is present, but only when the verification model of the safety layer or its constraints are violated. And we'll show both positive and negative test cases and show that collisions only occur when the safety layer model is violated, when the safety layer is in use. We'll also show an improvement to the safety layer design, which is using dynamic conformation with the integrated adaptive control, and that would be our 2 demo goals for this particular module. Could you go to the next slide, please? So while this is not necessarily something we can complete, but we are trying our best to do an integrated system where the robust object recognition, which will reduce the ML layer perception faults, as Simon discussed, and the safe lander from Professor Boli's group will be integrated into the overall system. And we'll showcase cases where, for example, the physical safety or the collision safety is guaranteed by the verifiable safety layer of the perception simplex. But then, for example, regulatory safety is handled by safe lander. So we are also trying to create such scenarios. And if we are able to complete this work, we'll demonstrate such scenarios too. As the last slide for our presentation, can you change the slide? We also wanted to highlight some of the collaborations that we have across the URI group. Of note, we are working with Professor Boli to first adapt the safe lander for autonomous air taxis and work with them to integrate that into the simulator and showcase that during the May demo. And of course, the overall simulator development has been a highly collaborative effort. Professor Hinjun Yun's group has been an equal contributor throughout this process. Same for Professor Naira's group. And we have also had contributions from many other groups in the URI. Thank you. Thank you, everyone, for listening to our presentation. Please let us know if there are any questions.
Actually, I want to make a short comment for the sponsor. One thing you heard about Ayush said is the notion about physical safety and versus regulation safety. What does that mean? Let me give an example. Let's say in the middle of the right, the self-driving car is the only car on the road, and there's no other vehicle or people or anything on the road. And there's a red light. So yeah, if you drive the red light, then you can prove you won't cause any collision or safety. But you still violate the law. It still is not permissible. So a lot of traffic rules actually look at aggregate. If you allow people to make a justification, can run the red light, sooner or later you will have a collision. The physical instance, the physical safety for collision avoidance is case by case. All right, so even you can achieve physical safety, doesn't mean that you have a license to run the red light or any other flight regulation. Okay, so that's set. Separate these two of fundamental importance from certification perspective. Because to certify a flight or airworthiness, you need verifiable algorithm. You need verifiable software. The algorithm has to be analyzable and provable. So that standard is being upheld in flight for years and reduce, actually make the air traffic, flight, one of the safest mode of travel. So the whole question is, do we want to replace this? I would say from the time horizon for ULI and its near-term extension, if there's any, replacing the entire certificate airworthiness certification are completely unrealistic and probably unsafe. There's a whole many legal issues. So to say certification in any person's career, say 10-year, 20-year perspective, I would say that we should maintain the current rigor in safety when we deal with public transportation. So that's set. The separation of the physical regulation with verifiable algorithms and optimize statistically. That's the way to go. So as you see, Ayush, can you show the graph picture once? Go back one, yeah, this. So the safe lander, next. The integration one. The safe lander actually is trying to avoid the violation of any traffic rules. Let's say, take everybody say not to run the red line, stop on the stop sign, something like that. don't driving too fast on the school zone level. I understand that's not right, but everybody understands it. Those are traffic rules. Pause. Those require the AI and vision. However, for collision detection and avoidance, there's a approval algorithm I already published and checked. We can do that without AI and ensure it. So we want to ensure at this point physical safety with a certifiable approach, satisfy the current FAA certification process. And then we do a best effort for AI, try to minimize, to keep the probability of regulation violation as low as possible. So the separation of these two actually is very important. If we want air taxi actually being accepted by the public and by the FAA, it is the compliance to the physical safety. Don't water down the physical safety. Because that's doable now through our research effort. And the AI is just great. It can help us to do regulatory safety in a way. That's no alternative. I hope that message.
Thank you,
can be
Louis.
clear.
Thank you. Right. So let's have also Evangelos present, because this is technical challenge 1 thing. And we switch now to Evangelos. He presents his demo plans. And by the end, if we get some time, we do discussion. I won't even think now about presenting our demos, but let's see what Evangelos presents. Evangelos, you are muted in case you are speaking. Unmute yourself.
Yeah. Let's see, let me share my screen. So I was asking if you can see me, hear me, and see my screen.
All good, yes, go ahead.
All good, okay. So I'm going to be very brief. I have 5 slides, and I want to talk about the demo that we want to do with Christos in May. And the main goal is essentially to have to test our covariance steering perception-based landing architecture on an actual hardware and aim to perform safe landing with perception in the loop. So we have 4 milestones, I think, and I'm just going to go through that. Just a quick reminder, what is covariance steering? There are algorithms that do trajectory optimization, and the way how optimization is done is by taking into account the second order characteristics of the uncertainty. And so when you try to find a trajectory that avoids all of the obstacles and takes you from a start state to a goal state, you do that for not only the mean, but also the covariance that arises from the uncertainties that you have in the dynamics of the system. And so what ends up happening when people use software optimizers out of the shelf that to set up their optimization, typically these problems end up becoming semi-definite programming problems or conic problems, is that this optimizers very often will give unfeasibilities. And so the question is how how one can generate a new optimization method that allows us to perform optimization for the mean and invariance of a dynamical system, but at the same time have the flexibility so that you can be feasible from an optimization perspective and have a working algorithm that is not going to crash, right? And so we have this work, and essentially what this work does is to use this very well-known method, which is called the alternate direction method of multipliers, or ADMM, that allows us to incorporate all of these constraints in the mean and the variance of the dynamical system. And then if I were to describe like the key idea is that essentially the algorithm allows you to be infeasible during the iterations, during optimization, but as you're approaching your optimal solution, that solution will always be feasible. And so we have tested that. We have done some experiments with hardware. The hardware was the Robotarium here at Georgia Tech. And we have good initial results that convince us that we want to really take this algorithm into real hardware. And so the first milestone is basically to use this optimizer as a planner that will provide the trajectories that will be tracked by a low-level tracking controller using the ONR Mini-Hawk vehicle. At this point, we will have perception, but we will not use the perception. We will just have the perceptual module only for data collection. And there are not going to be any obstacle constraints. So the objectives here are to just test the sync to real gap and perform the tuning that is required. There is state estimation, right? And then we have to be able to make sure that that part also works. And there's work to be done on calibrating the camera. And then ideally, we would like to do this task with running our optimizer in a rolling horizon optimization mode. So the problem is essentially fully observable, right? And that's a milestone that we have, which we want to be able to cross that milestone by the next 2 weeks. We have a trip to ONR in the second week of March. The second milestone is basically to now that we have a working feedback loop with a planner that runs in a rolling horizon optimization mode or in an MPC mode. Now what we want to do is we want to be able to use a camera, identify the spot that we want to be able to land, and use that information to guide our covariance steering planner, so that when the planner provides the trajectories, it makes sure that the mean and the variance of our state will be always within the boundary of the landing zone. And so there's a lot of work to be done here on the hardware capabilities, and of course integrating the perception within the feedback loop. That's going to be a big leap forward. And here we are talking about essentially experiments on the actual hardware, right? There is, at this point, there is no simulation. Okay, now milestone 3 is we're going to go and just make this problem a little bit more interesting. We have the perception in the loop to again identify the spot that we want to be able to land. And here we are going to essentially introduce virtual obstacles. And we are not going to use the perception to identify these obstacles. The goal here is to test our replanning process and see whether or not, our reoptimization really does what it's supposed to do, which is to provide trajectories that will avoid these virtual obstacles. Again, the perception here will be to identify the landing zone, and the obstacles here will be to actually change the solutions that the optimizer is giving us in terms of which trajectory to generate that will take us to the landing zone by avoiding the virtual obstacles that we have, okay? And then the fourth milestone is to essentially have the obstacles, the virtual obstacles. We have the perception in the loop for performing covariance steering in a rolling horizon optimization mode. But now, at this point, we will start creating physical barriers on the landing pad, or we may have like multiple landing pads. And the idea basically here is to just test the end-to-end covariance steering control architecture with active perception, and see how robust this architecture is in terms of disturbances that we have in the visual scene. Again, the objects here, because they are placed virtually, they are not going to be identified by the perception system. We can do that after May, but I think that's this milestone 4 is important to meet. So this is the the four milestones we have, and I'm really happy to answer any questions that you guys have. The learning module is essentially the perception module, and again, there is a real-time optimization that will take place in terms of providing the guiding trajectories using our covariance steering architecture. Yeah.
So let's see if we have any questions for Evangelos regarding these demos. If no questions, so we are left from Technical Challenge 1 team. And when it gets to our group, we showed already the integration with the simulator, the work that Luisa and Boli have been doing, and we have been collaborating with others also across the team. What we plan basically to show during these demos would be some videos from our lab. We're just trying to simplify instead of carrying our platforms to Reno all the way to reproduce the demos in the lab physically. We have the demos here in our lab, and we'll just record our videos and come to the demo days. So the plan for the demo days is that we will have 2 days demo involving visits to physical sites where these flight tests will happen. Some university-based agenda will include the demonstrations in the simulators, and we'll show the videos from our lab, and we'll have, of course, presentations accompanying and discussion as well. This will be a 2-day event. We are all excited, looking forward to it. Now I want Shenk to share some of the flight tests we had in our lab. We have new interesting unconventional configurations developed, like overactuated Omni drone that with its dynamics can be similar somewhat to urban air mobility vehicles in terms of overactuation and other type of developments. Shane, can you share the slides and just be quick, spend 5 minutes, show the new demos, what people have not seen, and we'll jump ahead.
Sure. Thank you, Nara, for this introduction. So I'll talk quickly about the demos we have prepared for this ULI demo day. So there are 3 major works that's going to be highlighted: L1 Quad, Div2, and an Omni drone. And for the sake of time, I'm going to jump to the ones that hasn't been presented to this group. So L1 Quad is the our group's architecture for quadrature robust control against a wide variety of uncertainties and disturbances. So you have seen the ground effect, you have seen the chip propeller, where we can handle this partial failure. So we have a recent work. So let me gonna show that really quick. So with L1, we can have this chip propeller drone flying stably. And then we were questioned about what happens if you have a complete failure on the vehicle. And then we managed to identify the key problem here, being that we need to reliably and fastly estimate or detect the rotor failure on board. So we recycled our L1 quad architecture and apply a multimodal approach to achieve fast, accurate, and robust failure detection. So what you see on the bottom is the video showing this capability where we're going to inject the failure. And then it's just too fast that we detect the failure within only 40 milliseconds. So the vehicle will now be handled by a fault tolerance control in the scheme and then land to the ground for safety reasons. So what happens among this 40 milliseconds is that we inject the failure, as you see on the bottom left, and then over the time, we can see the detected uncertainties with the fault propeller model is getting down, and then the 3P is getting bigger and bigger. And then within 40 seconds, once we reached this switching of the dominance of the two models, we detect that here is the failure. So we'll have something better edited. This is shot yesterday in the lab and then quickly edited without too much touching. But I think we have shown the capability of the fast detection we can do. And then this is the hanging weight, so I'm going to skip that. And then, yeah, this is something new that we did over the last year, which we collaborated with a team from Japan who has this deformable propeller that have the collision compliance. So the design they offered is the soft notice here that can make the propeller sustaining or surviving from collisions, which rigid propeller cannot do. But this design of propeller violates several design principles for controllers, which make the control really hard. So we applied the L1 quad architecture to their drone. And then together we show the capability of sustaining severe collision, in which case a student intruding this carbon fiber rod into the propeller path. You can see on the bottom material here that L1 quad can help the drone to survive and also getting back to normal flight condition. And this is really the interplay between advanced materials and robust control methods to really expanding the operational capability of aerial vehicles. And then there is the DiffTune, which I think we have shown the demo here. So I'm going to, again, walk quickly over this. So DiffTune is our in-house control auto-tuning architecture that can do efficient and optimal parameter search with model information. And we leverage to do the experiments on a quadrature for the auto-tuning of aggressive trajectory tracking task, in which we achieved 3 times error reduction in only 10 trials. And on the right, you're seeing the parameter evolution within these 10 trials that can be hardly done, say, manually by student or by me. So here is the demo that shows the evolution of the 10 trials we've seen in this aggressive tracking case, where you can see the tracking is getting better through the iterations from this completely not tracking to, in the end, a very fine tracking. And then we dive deeper into the scheme to see the generalization of the tune parameters and came to see that when you have tasks or trajectories that have similar motion characteristics in terms of speed or acceleration, then the parameters can generalize. And in terms of comparison, we can achieve similar performance of a student or hand-tuned parameter. So this indicates that we have good generalization in the tune parameters for the tasks that we didn't train or tune the parameters for. And then lastly, regarding this Omni drone, which is our recent build robotic platform that has this over-actuatedness, and also most importantly, it has the omnidirectional motion capability. As you can see, In this demo video on the right, this is Hyungyu doing the teleoperation of the drone, which is mimicking a future capability of aerial manipulation. And here in this work, we're pushing to the limits of what this vehicle can offer in terms of aggressive motion. And in this case, the motor dynamics or the specifics about the actuator is getting into our way. So we're designing a new controller that can handle the significant rotor delays during this aggressive maneuver. So you see that coming up next, we're trying to do this first simple task of translational motion only, where on the left, we're showing the baseline approach, which don't have encountered or don't consider the motor dynamics. And on the right, we have considered that with which help us to greatly reduce the tracking error. And and then we move to a pure rotational motion in this case, where you can see again with our consideration of the motor dynamics, we can reduce the rotational tracking error greatly than compared to the left. And then the last one is very interesting. We're trying to hover the vehicle or float the vehicle while doing aggressive maneuver. And here, with our approach, we can fix the vehicle to rotate in the place with a very small drifting. While on the left, you can see without that, this is barely maintainable. So that's pretty much it. I hope I'm still within time. And if there's any question, I'm happy to answer that. Thank you.
You're perfectly on time. So these are kind of the demo plans from Technical Challenge 1 team that includes control and perception. Next time in a month, we'll have Sayan, Mitra, and Chuchupam present the developments on their VERSE tool for verification validation for real-time autocoding. And then we will have the Technical Challenge 3 for fault detection, reachability analysis. And finally, we'll have the team from Technical Challenge 4 that includes also Sierra Nevada Corporation team with their big Volvo vehicle and Christos and Petros with all their demos. And that will be right before the demo days. So any questions, we're happy to answer. Take now. No questions? Okay, if no questions, then see you in a month, right? In 4 weeks. In the meantime, certainly there can be email exchange with questions or concerns regarding these demo plans. By the way, Evangelos and James Ramsey from Lockheed Martin worked on this demo plan. So we're thankful, really, James, for reaching out and helping us. And of course, Lockheed Martin will show their flights with the Vista, I believe, in during the May demo days. They will have their presentation. Thank you all. See you in 4 weeks.
Thank you. Bye-bye.
Thank you.
Bye.